Welcome back to our IB Physics video series. This is the second and final video in IB Physics Topic 6, Circular Motion and Gravitation, where we will be looking at Newton's law of universal gravitation and gravitational fields. In our previous video, we mentioned that gravity can be regarded as a centripetal force. But what is gravity? Well, let's discover this by looking at Newton's law of universal gravitation. This law states that every mass in the universe attracts every other mass in the universe. This occurs because every mass releases gravitons that exert the gravitational force on other masses. The more mass there is, the more gravitons are released, and thus the higher the exerted gravitational force. However, the further away the other mass, the weaker the exerted gravitational force. If you remember, this is very similar to how the electrostatic force behaves. The formula for gravitational force is given by force equals universal gravitational constant g times mass 1 times mass 2 divided by radius squared, where radius relates to the distance between the two masses. In this, g is equal to 6.67 times 10 to the minus 11 newtons per meter squared kilogram squared. Let's try this in a practice question. Two masses are 50 meters apart and have a gravitational force of 12 times 10 to the minus 8 newtons. If one mass is 4,000 kilograms, what is the missing mass? For this, we use our equation, force equals gravitational constant times mass 1 times mass 2 divided by radius squared. So, substituting in the values of force, the gravitational constant, mass 1 and radius, and then solving for mass 2, we find that it is 1,100 kilograms. Although the gravitational force is present between all objects, you likely know yourself that this is not felt unless the masses are huge. For such masses, let's explore how we describe gravity via their gravitational fields. Like an electric field is the area wherein there is an electrostatic force per unit test point charge, a gravitational field is defined as the area wherein there is a gravitational force per unit test point mass. The strength of this gravitational field G at any point is the force exerted per unit point mass, measured in newtons per kilogram or meters per second squared. On Earth, the gravitational field strength is 9.8 meters per second squared, a value you should memorize for exam questions. The formula for gravitational field strength experienced is thus gravitational field strength equals gravitational force divided by mass. This is colloquially known as weight divided by mass. Note, mass is denoted with a lowercase m in this formula. On the other hand, the formula for gravitational field strength exerted is gravitational field strength equals gravitational constant times mass divided by radius squared. Note, mass is denoted with an uppercase m in this formula. Let's solidify our understanding of gravitational fields with a practice question. An 80-kilogram astronaut is standing on Jupiter's surface. Jupiter has a mass of 1.9 times 10 to the 27 kilograms and a radius of 71,492 kilometers. A. What is the gravitational field strength of Jupiter? B. What is the experienced gravitational force of the astronaut? For A, we are asked to solve for the exerted gravitational field strength. So we use the formula gravitational field strength equals gravitational constant times mass divided by radius squared. So, substituting in the values of g, Jupiter's mass, and Jupiter's radius, we can solve for a gravitational field strength of 25 meters per second squared. For B, we are asked to solve for the astronaut's weight. So, weight equals mass times gravity. Thus, substituting in the values of the astronaut's mass and Jupiter's gravity, we can solve for weight as 2,000 newtons. Obviously, this would crush the astronaut. But thankfully, this is a hypothetical physics problem, so we'll ignore that. Now you know how to calculate the experienced and exerted gravitational field strength. But what happens when a mass at equilibrium experiences a gravitational force from two different objects, such as a satellite between the Moon and Earth? This is a common scenario the IB expects you to be able to solve. Let's quickly discuss the situation. Masses 1 and 2 both attract mass 3 towards themselves. Using the formula for gravitational force, we can find the forces on mass 3. Knowing that the mass is at equilibrium, the gravitational field at the mass must be 0, thus we can equate the formula and cancel like terms. This leaves us with the formula mass 1 divided by radius 1 squared equals mass 2 divided by radius 2 squared.
You've now reached the end of the preview for this IB Science video. If you want to check out the full video, head over to our website and select a membership plan today.